Okay, for the next topic, which we will have with matrix equations, um, we're going to be intertwining matrix equations with what we have been previously looking at with vector equations. So again, just providing a bit of a segue, going back to vector equations, we had that B was equal to a linear combination series that we have between x and a, where we have x1, x2, all the way up to x of n are referred to as the weights, and we have our a of 1, a of 2, a of n. Those are the vectors, or in this case, where you have one column matrices, and we have for the augmented matrix form of what we have representing the linear combination. Again, you have your vectors a of 1 all the way up to a of n, and of course you have equal to b. And b can be generated by a linear combination from a of 1 to a of n if and only if there exists a solution to the linear system according to the augmented matrix. And so we have again, we have the linear combination, so we have b is equal to x of 1, a of 1 plus x of 2, a of 2, all the way up to x of n times a of n. Now for the matrix equation, okay, again, we have ax is equal to b. And if we had the A as an m by n matrix with columns going from a of 1 to a of n, and again, each of a1, a2, all the way up to an, again, those are going to be one column matrices. And if x is equal to Rn, okay, n is going to be reference to the number of columns, and the subscripted values you have to be positive integers or natural numbers. And if we have these conditions, then the product of a and x, which would be referred to as ax, is going to be the linear combination of the columns of a using the corresponding entries in x as weights, whereupon we have x of 1 times a of 1 plus x of 2 times a of 2, all the way up to x of n times a of n. So you're going to have a bit of a visual pattern. Okay, so you're going to have that x of 1 will be mapped with a of 1, we have x of 2 mapped with a of 2, and we have going all the way out to x of n times a of n. So again, we're looking at linear combinations. And for the combinations to come out to a definite solution, okay, I made this note that the number of columns in A and the number of rows in X must be the same. Otherwise, there will be no solution. And for what we have for the following, okay, say if you have one element vectors, where we say we have A1 is just going to be at 1, and you have A2 at 5, so you have A, you have 1, 5, and next we have 4 and negative 7, so 4 would be like your x of 1, negative 7 would be your x of 2. And if I go with the pattern x of 1, a of 1, so I have 4 times 1, x of 2, a of 2, I have negative 7 times 5. And if I multiply, 4 times 1 is 4, negative 7 times 5 is negative 35, and combining, we have for B, this would be the one element matrix, which we have at minus 31. And if I have 1, 5 times 4, negative 7, 1, again, there is a mismatch between the number of rows in A and the number of columns that we have for X, okay, and so there is going to be no solution, okay. And for what we have in this particular case, right, so the number of columns in A and the number of rows in X must be the same. And now for what we have in the third case, all right, so you have A, we have consisting of 1, negative 1, which will be A1, 2, 4, which will be A2, 3, 6, which will be A3, and X will consist of 2, 1, 5, and in the positions, okay, we have X of 1 at 2, X of 2 at 1, X of 3 at 5, and we have, again, so just mapping together X of 1 with A of 1, so I have 2 times 1, 1, X of 2 with A2, so I have 1 times 2, 4, and X of 3 with A3, I have 5 times 3, 6, and distributing, okay, so we have 2, negative 2, and still I had the maintaining of 2, 4, and 5 over 3, 6, I have 15, 30, and we have 2 plus 2 plus 15 comes out to 19, negative 2 plus 4 is 2, plus 30 comes out to 32, and that will be the result we have in B. Now, for what we have for some of the further details, okay, and there's going to be a frequent intertwining between the matrix and the vector equations. If A is an m by n matrix, and B is in Rm, where m will be the number of rows, and when subscript to m is going to be equal to, just like n, you have positive integers or natural numbers. Okay, and so if we have these, then the matrix equation Ax equals B is going to have the same solution set as the vector equation, which has the same solution set as the system of linear equations whose augmented matrix is, once again, you have bracketed, you have A1, A2, AN, again, where each of the subscript to A's is in reference to a vector, and we have equal to B. Now, just testing out, like for consistency. Say if you have A at 1, -4, and 3, -12, and we have B consisting of B1 and B2. And you might have the question posed as Ax equal to B consistent for any vector B. And so just looking at what we have, setting up what we have in the vector equation. Okay, so we have 1, -4, 3, 2, and just making a note, A1 is equal to 1, -4. Second column we have A2 equal to 3, -12. And applying what we have for the matrix equation. So we have x1 times, okay, the first column, x2 times the second column, or the second vector A2, and we have equal to B, which we have at B1, B2, and expressing what we have here as an augmented matrix. So you have 1, -4, 3, -12, and B1, B2. And looking at taking what we have here and applying reduction along the lines of echelon form. So I had the upper left hand corner consists of 1, so we have our pivot position in the upper left hand corner at 1, and I want to make the -4 beneath it a 0. So I can make adjustments by adding 4. So this will be done by taking the second row and adding 4 times all the corresponding elements in the top row. So you have R2 plus 4 times R1. So we're going to have, so we still have 1, 3, B01, so I did not apply any treatment to the top row, but for the second, we'll end up with -4 plus 4, -12 plus 12, and of course we're going to have, to B2, we're going to have 4B1 added, and if you notice we have 0 is equal to 4B1 plus B2, and now the equation Ax equals B is not consistent for every B, because some choices can cause 0 to not be equal to 4B1 plus B2. And also, another way of explaining this, and we'll get to the fundamentals in just a moment, okay, it's not consistent also because not every row has a pivot position, and it must. Again, I will be looking, explaining that just a little bit further. All right, so for what we have in essence, okay, the equation Ax equals B is not consistent for every B because the echelon form of A has a row of zeros. Okay, so just another way of wording here. And now, so we're going to have encapsulated, okay, for A, the following statements are either all true or all false. And for each B in Rm, Ax equals B has a solution. And if that is true, then each B in Rm is a linear combination of the columns of A. And if that is also true, then we have the columns of A span Rm. And fourth, okay, and this is where this last example failed, and we had that A has a pivot position in every row. Okay, so if it does, and if you have a row of zeros, then it's not going to pass the litmus test. But again, collectively, either these statements are going to be all true or all false.